Yeah, I guess it's just that the one who created the the conference is also interacting with it. Yes.
Hi, everyone, and welcome. It's so great to have you guys out here today, and also big welcome as well to everyone joining online. Thanks for being part of today's session. Today's talk really brings a fun, exciting mix of creativity and computation, design and technology. We're so excited to have with us Dr. Adrien Bousseau, Senior Researcher at Inria Université Côte, working with the GraphDeco research group. Adrien's research focuses on image creation and manipulation, especially drawings and photographs. Over the years, he's worked on everything from image stylization and editing to vector graphics and sketch-based modeling. His work has earned him several awards, including Eurographics PhD Award, a Young Researcher Award from the French National Research Agency, and both ERC Starting and Proof of Concept grants. So without further ado, please join me in giving a warm welcome to Dr. Adrien Bousseau.
Thank you very much, and thank you for joining today. So indeed, I'm doing research in computer graphics and in particular 3D modeling. And one topic I explored over more than a decade is how to create 3D shapes by drawing. And that's what I will describe today. So I will give you an overview of research over more than 10 years, but I think it gives a good idea of how we progressed on those topics. And the motivation for looking at drawings and 3D shapes is that despite progress in digital tools, drawing is still a very popular tool for designers because it allows them to very quickly express their ideas and with a lot of freedom. And that's true in many domains, including industrial design, but also architecture or fashion design. But while drawings are great to communicate with collaborators and clients, a drawing alone is not enough to evaluate the feasibility of a concept. So that's why drawings are often converted into 3D shapes for 3D engineering. For instance, to run physical simulations, let's say to see if the boat can float well. And so in practice, designers and engineers often have to go through several iterations, alternating between creative exploration and physical validation. And for that, they need to alternate between drawings and 3D models. But converting a drawing into a 3D model remains a tedious manual task, and it's a bottleneck in this iterative process. And because of that, many concepts are actually not explored as much as they should be because converting them to 3D shapes is costly. So the ambition of our research is to facilitate or even automate the creation of 3D shapes from drawings. And here I'm showing a long-term vision. We are not there yet, but ideally we'd like designers to be able to draw the shape they have in mind and immediately have some feedback, let's say, on the aerodynamism of this car. So combining physical simulation with drawing in this creative process. But to reach that goal, a fundamental challenge is to recover 3D information from 2D drawings. And it's a nil-post problem because if we just look at how a shape can reproject, any point on the drawing can lie anywhere in depth. So while we perceive a 3D chair in this drawing, actually a distorted chair would be equally valid if we just look at reprojection. So that's why today I will present a mathematical formulation of 3D reconstruction, which combines two terms. The first term is reprojection. We still want the 3D shape to align well with the drawing, but we need to complement it with other types of priors on the shape we are looking at. A common prior in sketch-based modeling is to assume that we are drawing smooth shapes. That's been proposed early on by Takeo Igarashi in the TEDI system, and it's been improved since then. And that's indeed a very good prior for organic shapes like balloons or pillows, because indeed they are smooth. And so if you have a 2D drawing, you can get a 3D shape that is smooth just by inflating it. So it's good for organic shapes, and it's good for novices who can quickly draw the silhouettes of the shapes. But the drawings we're interested in are often much more complex. They not only have smooth surfaces, but also discontinuities. So on the one hand, it makes the task harder, but on the other hand, we can leverage richer information. And in particular, if we target professional designers, they have been trained to depict 3D shapes effectively in their drawings. And that's done through several techniques. So if we look closely at this drawing, you notice that some of the lines actually tell us about the perspective. This grid gives us information about the vanishing points, and that's enough to calibrate a 3D camera and get already a first information about the 3D shape. Other lines depict curvature, so it's very helpful to reconstruct curved surfaces. And so that's what I will focus on today. How can we exploit and leverage the drawing techniques that designers master to recover the 3D information that they are trying to depict? So this idea has been already considered in prior work, but mainly for interactive systems. So in I Love Sketch, designers can quickly create 3D drawings, but they need to master a very specific interface. And same for the right on the work on the right. So we are inspired by this type of systems, but we are trying to automate them further to give extra freedom to the users. Ideally, we'd like our users to draw as they draw on paper without having to conform to a specific user interface. But if we try to automate this process, then we face extra ambiguity, because I explained that different types of lines can give us information about the 3D shape, but when people draw, they don't necessarily think about what type of line they are drawing. They don't use a different pen for the grid lines or for the curvature lines. So that means that if we want to impose geometric constraints on the drawing, we need to identify what type of lines are drawn, and that's an extra type of unknown. So we model it with binary variables that will indicate for every, let's say, stroke or point in the drawing, whether some geometric constraint should apply. So that gives the most general formulation of line drawing reconstruction, a combination of an alignment term, like the reprojection, and several geometric constraints with binary variables to decide when those constraints should apply. So this is very general, but also very hard to solve because we have a mixture of continuous and binary unknowns. And so it's a combinatorial problem that needs custom solutions to be solved in a scalable way. And that will be the topic of this talk. I will walk you through a series of work that try to solve this formulation first in a very narrow domain, and progressively we'll see how we expanded the scope of our solutions. So the first paper I will present is actually quite old, but it illustrates well the overall methodology that we then adopted for subsequent projects. So that's why I'd like to present it still, because it's very didactic. So in this collaboration with University of Toronto and UBC, we propose a methodology that consists in first studying how people draw to better understand the techniques they use, but also how people perceive drawings. Because ultimately, drawings are not like photographs. They are created by humans to communicate with other humans. So the techniques that designers developed have been very well influenced by how people perceive drawings. And by studying the two literature, we can actually confirm our hypothesis and have more information about how to interpret drawings. And once we've gained this understanding, we can try to formulate geometric constraints suitable for numerical optimization. So specifically in this project, we studied a specific drawing technique called cross sections. They are very helpful to convey curvature. So if we look at the shape on the left, which is a very early sketch of a suitcase, the orange lines, which are those cross sections, help us a lot perceive the bump on the front side. If you didn't have those orange lines, it would be very hard to understand what this shape is. Or same on the right, those two quads, one is convex and the other one is concave. And you do make the difference thanks to the cross-section lines in the middle. And that's well stated in the textbooks about design sketching. They do say that cross-sections explain curvature. So now can we confirm this hypothesis with perceptual studies? Well, indeed, people have studied how people perceive intersecting lines in a drawing, and we can do the test together. So I will ask for your participation. I'd like you to tell me what 3D shape you perceive in this drawing. Yeah, do you agree? So indeed, most people perceive a cylinder, meaning that you've interpreted the arc as the direction of maximal curvature and the straight line as the direction of minimal curvature. So we can do the test again. This time, what shape do you perceive? Yeah, people say a flattened sphere, and that's indeed what most people perceive. Just for fun, we could actually draw the same lines on the cylinder. But that's not what you would favor as an interpretation in the absence of context. And designers don't try to trick their audience. So they will never draw such a drawing. They will prefer to draw the cylinders with those two lines. And that's really what we are building on. We are not looking at random lines. We are looking at lines that have been drawn with a purpose. Okay, so we are quite confident now that those lines depict directions of principal curvature. So now we can turn to differential geometry that tells us that the two directions of principal curvature on the surface are always orthogonal. So now, through this study, we end up with a very concrete mathematical constraints. Every time we'll have two cross-section lines intersecting in a drawing, we know that they should be perpendicular in 3D, and we can express that with an equation, the dot product between their tangents. So I walked you through all those steps, but we applied the same methodology for different aspects of cross-section lines. So we observed that they are often on orthogonal section planes. They delineate local symmetry. And we also noticed that people don't draw from arbitrary viewpoints. They often choose viewpoints that minimize foreshortening. This way, all sides of the objects are shown equally, and so it's easier to understand the shape. So for all of those properties, we derived geometric constraints, either on the normal of the section plane or the tangents of the curves we are interested in. And so we can now plug that into our formulation. So we have a 2D drawing at inputs, we know the 2D tangents, and we solve for the cross-section planes. So the plane normal, the plane offset, and the depth of the tangents. And so all of those are subject to the reprojection term, the first term in my equation. And then the second term, the geometric constraints that we leverage are orthogonality, symmetry, and minimal foreshortening. So we could fill in the different elements of this equation based on our study of how people draw and how people perceive. In this very first work, we didn't solve the problem of identifying when constraints should apply. We did ask the user to use different colors for the different types of lines. But thanks to that, we could solve for the section planes, then find the orientation of the surface at each intersection of the 3D planes, propagate this information along the curve and within the drawing, and that gives us what we call a normal field. So it's not a complete 3D shape, it's just the orientation of the surface, but that's enough to compute shading automatically. So we've done one step forward. We are not yet automating 3D modeling, but we can greatly accelerate exploration of different appearance of these objects, because all of those drawings have been shaded automatically now. All right, so that was just to really illustrate our methodology. Now, how do we go beyond the surface orientation? Well, in a follow-up work, we actually try to inject a few more geometric constraints. So in addition to the orthogonality of the cross-section lines, we also looked at parallelism between adjacent lines, planarity, and others regularity that are very common in industrial products. So we can frequently find them in design drawings. But this time we try to address our core challenge, which is to identify when those constraints should apply. And to do so, we propose an algorithm that we could see as an iterative rounding. So we start with an initial guess, which we get from our cross sections, because this is a constraint we trust well. Every time we have intersecting curves, we'll make sure they are orthogonal. But if we look at the reconstruction from the side, which is shown on the right, it looks a bit distorted compared to what you perceive on the left. And that's just because drawings are not very accurate. People don't follow geometric optics as precisely as a real camera. So even if we impose orthogonality, it's not enough to correct all of those little mistakes. But it's still a good guess. So now that we have a first initial 3D reconstruction, we can detect whether other constraints could apply. So if we look at parallelism between adjacent lines, in this 3D reconstruction, indeed, the light green lines are almost parallel, while the two others I highlighted are far from being parallel. So we'll use this 3D measure as a weight on our constraints. So we can measure it on any pair of adjacent lines, and we can add that as a confidence in our equation. So instead of a binary unknown that will either impose the constraint or relax it completely, we use a continuous version, which will try to apply these constraints with a weight that depends on our confidence. And so now we can update the reconstruction. And so if we repeat that process progressively, the constraint that can be satisfied will emerge, and the ones that are hard to satisfy will just vanish. So that's why I call this an iterative rounding. We try to snap the variables to 0 or 1. And so here is the progression of the optimization, where at the end we obtain a very regular reconstruction. And so here is a video of the optimization in progress. We see that at the beginning, the shape changes a lot, and then progressively it converges, and we see sometimes an abrupt change. That's when the constraint is snapped to impose, let's say, parallelism or so on. And so here we drew only half of the object, but then by symmetry, we can actually produce a complete shape. So this was the first work that we developed that will really allow us to take a real drawings from a textbook, trace some curves over it, and get the full 3D reconstruction. So this is one example, another result. But the limitation is that we need to trace, because all the terms I explained require some clean vector curves to compute parallelism, to compute orthogonality. And so that was actually what I think prevents this type of tool to be used in practice, because sure, it's quick to draw something freehand, but it's tedious to trace vector curves, as tedious as doing 3D modeling directly. And in addition, one aspect I didn't comment on yet is that if we look at intersections in a 2D drawing, some intersections indeed depict connections between lines that should happen in 3D, but some intersections are actually just due to occlusions. One line is behind another one, they should be separated in 3D, but they project and they occlude together in the drawing. And that's an unknown we didn't know how to solve at the time. So we asked users to click on intersections that should be ignored. But again, that's very tedious to click on every intersection of the drawing. So to summarize, this was again a good step towards 3D modeling, but there was still some unknowns that prevented it to be fully automatic. And really far from the real drawing that people draw that I show on the right, which are much more complex, lots of pen strokes, lots of occlusions, and so on. So that's where we realized that if we wanted to progress on that problem, just looking at the dozens of drawings from textbooks would not be enough. We needed to scale, and to do so, we need to invest in data collection. And so we conducted this study with collaborators from TU Delft, who are design professors. And together with them, we could actually work with their students and their former students to collect real design drawings, not at a scale that would be enough for machine learning, but at least at a scale that will allow us to have a benchmark. So this was the data set we call OpenSketch. And it was filling a gap in the literature. There's been some work on collecting drawings for different graphics applications, but they target often a very different domain. So the work on the left targets little drawing that anyone could draw, but very far from what a professional designers would do. The one in the middle is focused on portraits, again, very different from industrial design. And on the right, it's mostly clip arts. The type of drawing we want to understand are concept sketches. So those are drawings that designers draw when they have a good idea of the shape in mind, and they want to explain it to typically engineers or 3D modelers. And so they draw them with very custom techniques to achieve accurate perspective. So they are well documented in different textbooks, but there are no data set of such drawings. So that's why we collaborated with design teachers from TU Delft. They know very well those techniques because they teach them. So they could first help us better understand why people draw that way, but they could also help us collect, well, first design a task and collect drawings that are representative of what people draw in the real world. So the task we designed together is actually something they give to their students in class, which is to show 3 orthographic views of a shape from the front, the top, the side. And then the student has to draw the same shape from a new viewpoint. So it's very different from drawing from observation. The students cannot just copy the line they see. They really need to visualize in their minds how the shape will look like from a different angle. And actually, to achieve accurate perspective, they will construct the shape. And that's what you'll see in this video, because we record every pen stroke, and you see that the designer starts by drawing what they call scaffolds, which are straight lines, boxes, that allows to lay down the main volumes. And then within the scaffold, using the straight lines as references, they draw the actual curves. And that's how designers draw in perspective accurately. And thanks to a pen tablet, we could record this entire information. So we don't only have the final drawing, we have all the steps that people follow to create it. And so we did that for 12 different shapes that we designed to be representative of the different geometric configurations that are quite common in everyday objects. So from very simple boxes to free-form surfaces and more complex shapes like the mixer. And then we hired both design students and professional designers to have also a representation of different styles, like different people draw differently, and we wanted a benchmark that will cover this variability. And so this is just a little snippet of what type of drawings we collected. As you see, there's very different styles, different level of detail, different shapes. So in total, we have 400 drawings, which allows us to observe this diversity. On the downside, it's only 12 shapes. So it's quite limited in terms of whether it's not enough to do machine learning, for instance. We only used it to understand how people draw and to test our methods. But it's still the biggest data set in that domain. If you look for professional drawings, you won't find bigger, to my knowledge. And the reason is that it's costly to collect because professional designers, well, you need to pay them, but they are also rare. It's not so easy to find participants, much harder than anybody who can hold a pen. All right, so then we manually labeled the different types of lines. Again, thanks to our colleagues, we could identify a taxonomy of different lines. So some are used to depict the sharp features on the shape, like the ridges, the valleys. Others are only used for construction, and sometimes they are not even on the shape, they are around the shape. And remember that we could record the drawing sequence, so we can study how different techniques are used at different stages of the drawing process. And so in particular, if we plot how different techniques are used in time, we see that people often start by drawing the scaffolds, which are those straight lines to specify the main volumes, and then they use those lines to draw silhouettes and creases. And that's an observation we leverage to design a new algorithm, which I will present now. So now that we have real data, we can try the hard work of reconstructing them automatically. And so we developed an algorithm that really leveraged this observation that people first draw scaffolds or cuboids, and that's good for us because those cuboids have a lot of regularity. Most of the lines are perpendicular, parallel, and I showed earlier that we know well how to reconstruct those. And then once those lines have been reconstructed in 3D, we can see how they intersect with curved strokes, which are a bit harder. So now for every intersection of a curve with the straight lines, we know where to place those intersections in 3D. The challenge is that, again, in a real drawing, due to occlusion, some intersections are actually should not be preserved in 3D. So, for instance, the green intersection is depicting a cubic corner. This is a real intersection in 3D. But the red point here is just an intersection due to occlusion. The curve is on the front side of this shape, while the straight line is on the back side. If we keep them connected in 3D, we will never get 3D. It will remain flat because they should not be connected. They should be separated. And so this is the hard problem we try to solve in this work. Can we detect which intersection is real and which intersection is only due to occlusion? But it's a hard problem because if we naively look at every intersection and try the two options, we have a huge combinatorial space to explore. So to cope with this scalability issue, we propose an incremental algorithm. Instead of trying to reconstruct all strokes at a time, we progress through the drawing sequence and we reconstruct one stroke at a time using what's been reconstructed so far. In case of ambiguity, we might actually explore several options. So that's why actually what we are performing is a tree search. We are searching over the tree of possibilities, but we'll try to trim that tree as quickly as possible to avoid a combinatorial explosion. So I will illustrate this algorithm now on a simple example. So I will work through the main steps, but mainly we are trying for every stroke to lift it to 3D by exploiting intersections with previous strokes. And then we'll use our constraints to select the candidate that is the most plausible. And that's how we solve for all those unknowns jointly. So let's do it together. This is a toy example, but it helps understanding the algorithm. So let's assume that we have already reconstructed in 3D the black lines. And now we're interested in this new line, the blue one that's been drawn, and that goes through 3 intersections, A, B, and C. We want to jointly place this blue line in 3D and decide if we should keep A, B, or C as real intersections. So if we let the line go through A and B, then it gives us candidate 1. If we instead let it go through A and C, we have candidate 2, and through C and B, we have candidate 3. So I'm again asking your participation. Which of those candidates seems the best in your opinion? You hesitate between candidates, the candidate 2. And why? This is how I interpret the to start with, yeah. But do you have an idea why you don't like candidate 1 or 3? In which sense? Any other have some idea of why candidates 1 and 3 are not so good? So usually people say that, well, the line is extending too much. If the designer really wanted to draw from A and B, they will not shoot the line all the way to C, right? It will be too much overshooting. True, when people draw, they overshoot a bit, but not that much, because then it gives a very ambiguous drawing. Remember, designers don't try to trick their audience. So if they wanted to join A and B or C and B, they will not extend to join the third point. So indeed, good answer. We prefer candidate 2 based on trying to keep the drawing well connected and not extend more than needed. Okay, so we've lifted the stroke. Let's move on to the next one. Now we have this purple stroke that goes through A and B. Again, there are several options. Maybe it's just a vertical stroke that only goes through A, or that only goes through B, or it joins A and B. Do you have any idea of which one is better? Any opinion? So you will prefer candidate 2. Is there any agreement? You agree? Usually there's no strong agreement, and that's what I expect. Because, yeah, we lack visual cues to decide. When that is the case, our algorithm just delays the decision. Either if, according to our score function, if there's no high score, or on the contrary, if there are multiple high scores, we cannot take a safe decision. And remember, since we are building one stroke at a time, if we take a bad decision, then everything else might get wrong. So we prefer to delay the decision. So let's just add one more stroke. Now, I show you a few more candidates. Do you have one that you think is better? Candidate 1, is there any agreements? Since you wanted, you choose candidate 2, do you want to change your mind? Yes? Good. So the reason why we prefer candidate 1 is that suddenly we have all the regularities we like. It's well connected, there's parallelism, there's regularity, it's a nice square. Good. So that's all I wanted to convey. We go through the sequence one stroke at a time. If there's ambiguity, we delay, but as soon as we can take a safe decision, we'll take it to avoid the combinatorial explosion. And so now this is the same algorithm, but on a real example. So you'll see how each stroke is reconstructed one at a time. At first, the main box, and then later on, the curves. It's not perfect. You'll see that some strokes are a bit floating around, but it gives a good overall idea of the shape, knowing that this was done on a drawing that was done completely freely by a designer even before we developed that algorithm. Compared to prior work that first developed a system and then asked designers to draw within that system, we did the opposite. We first asked people to draw as they like to draw, and then we developed an algorithm that can deal with this data. So here we're showing some slide view changes. As I said, you'll notice some sliding. The strokes are not always very well attached. But I must say that we were quite happy when we reached that result, because this is the first automatic algorithm that can lift real drawings without any constraint on how those drawings were created. Apart from following the usual drawing techniques like using scaffold and so on. All right, so we then improved on that work by adding an extra constraint, which is symmetry, which on the one hand limits a bit the family of shapes we can deal with, But in practice, symmetry is so common that it turned out to be very helpful for that problem. And so just to give you a little teaser of what it can achieve, this result was achieved by the algorithm I just presented. So we get the oval shape of the chair, but you see that one stroke is floating around. And as we turn, we notice that the seat is actually not really rectangular. It's shaped like a prism. While if we account for symmetry, we can get much better because, yeah, this is a symmetric shape. The seat should be symmetric. A square is a much better interpretation. So how do we achieve that? Well, we try to leverage symmetry, but not just global symmetry. Actually, if we look at objects around us, there is a lot of local symmetry as well. So some parts are symmetric, even if the entire shape is not symmetric. So here I'm just showing some of the symmetry planes that we could detect in those drawings, and that can help us lift the drawing to 3D. So how do we proceed? So we have, remember, our drawing sequence as inputs. What we'd like to find is local symmetry planes and correspondences with respect to that symmetry plane. So for instance, the two wheels are symmetric with respect to the green plane. But those can be partial symmetries because people don't always draw the exact same strokes on each side. You could have a long stroke on one side and two short strokes on the other side. They do represent symmetric parts, but they only match partially. And that would be a challenge for us. If we look at prior work, especially in computer vision, symmetry has been used a lot, but often on points rather than lines, and even less so on curves. And well, when people deal with points, they don't have partial symmetry because the point is either a perfect match or not, while with curves, you need to account for partial correspondences. And also, most prior works only considered a single global symmetry plane, while we want to deal with local symmetries. So I will not detail how we detect the symmetry planes. Let's assume that we have them. How can we use this information to lift the strokes to 3D? So let's start with a very simple example. We have this cube. We are interested in the yellow and purple pen strokes. And we assume they are symmetric with respect to the green plane. Well, that's enough to place them in 3D because we can, knowing the camera, we can basically push the strokes in depth until they are symmetric with respect to that green plane. And there's only one depth that satisfies these constraints, so that's enough to solve our reconstruction problem. But that's only if those two lines are indeed symmetric. If we pick two lines that should not be symmetric, let's say those two purple and pink strokes that are on the front side, we can always place them in depth such that they are symmetric. If we push the purple line behind the green plane, we can make it symmetric with the pink one, even though when we look at the drawing, we see that they are both on the front side. But if we only look at the individual strokes, there's nothing that tells us that this part should be on the front and this part should be on the back. So this is just to say that if we try every pair of strokes, then in many cases, we can't find a 3D interpretation that will be symmetric. It's just that it will be wrong because we picked the wrong pair of strokes. And so that's what happens if we are naive. If we select all possible symmetric correspondences, we end up with a cloud of 3D pen strokes. Some are good, but many are misplaced. And so our task will be to only select the good ones. So we have a way to create many candidate interpretations just by trying any pair and imposing that they are symmetric. And from this large set of candidates, we try to select a subset. And we now back to a more standard discrete optimization problem. We can assign a binary variable to every symmetric correspondences and solve for this value so that we set it to 1 if we want to keep that correspondence, and we set it to 0 if we want to remove it. And our objective function will be to maximize the overall symmetry. So if we do that, we can indeed, oops, I went too fast. We can indeed remove most of the candidates and end up with a very symmetric shape. If we only do that, you notice that on more complex shapes, we still have some problems because some strokes end up misplaced and disconnected. That's because in this first version, I only used symmetry as a visual cue to lift to 3D. But remember that we have other cues like connectivity. Many strokes connect to form cubic corners, so they form triplets of strokes connecting at the same point. That's something we can exploit. And we also said that strokes should not overshoot too much. So often they are bounded by their 3D intersections. So if we account for those extra cues, which are mainly about connectivity, then we can have a very good reconstruction. So our algorithm actually solves for two binary unknowns, one to decide which symmetric pairs should be kept, and one to decide which intersection should be kept. But because we have a way to pre-compute all the candidates, we can frame that as a global optimization. So compared to the previous method that needed to process the sequence one stroke at a time, we now are able to formulate this reconstruction as an integer program. So it's a global optimization that will process all the strokes together. So I won't go too deep into the details, but basically we want to maximize symmetry and connectivity. And we have constraints mainly to make sure that when we select some symmetries, they are compatible together. So if, let's say, what was a good example? Yeah, so if stroke A is symmetric with stroke C and B, the resulting 3D we obtain for each of those should almost align. Otherwise, the stroke should be placed in two different depths, which is impossible. So we model those constraints in the optimization. But to summarize and then to give you the main intuition behind these methods, we can pre-compute the 3D position of the strokes, which is the continuous unknown. So we pre-compute it just by trying every candidate. And then we only solve for the discrete unknowns, which is select which of those candidates should be kept to create the final 3D shape. And it works surprisingly well on very complex drawings with lots of over-sketching. Really the type of thing we could not do in the past when we had to trace everything. Now we can automatically lift those strokes to 3D. So this shape is particularly well suited because there's a lot of straight and symmetric lines. But this one is a bit more curved and incomplete. Oops, this went too fast. And still we do manage to reconstruct it thanks to all the symmetry it has. This one is more challenging because ellipses are very hard to draw accurately. So in practice, they are quite distorted, but overall, we do get a sense of the cylinder of this hairdryer. And I particularly like this one because it's more representative of the type of shape people would like to design. It has curves and straight lines, and they are, again, quite well placed. So we don't have a complete 3D surface like a triangular mesh, but we do get a good cloud of pen strokes. And then the next steps could be either to automatically surface those strokes. So we did some work on that topic. Inspired by what people do on point clouds, we adapted those methods to what we would call a stroke cloud. Or this reconstruction can already serve as a very good reference for people doing 3D modeling. In the current workflow, designers will create 2D drawings, and 3D modelers will use those drawings just as a visual reference. Now, by lifting them to 3D, we give them a much better reference that they can load in their 3D modeler and then model around it. All right, so that concludes my presentation of this stream of research. In conclusion, we formulated 3D reconstruction as this global optimization that combines discrete and continuous unknowns. And through the years, we managed to develop a general algorithm that jointly solved for the depth of the strokes and which constraints should apply, symmetry, connectivity, and so on. How we manage it was to really study how people draw, collect real drawings, and design custom algorithms that leverage this domain knowledge, specifically leverage some of the techniques that people draw, but also the order in which they draw. And so here I'm just showing that indeed it took quite some time. This is not my only topic of research, so I did other stuff in parallel, but just to realize that because it's not a mainstream topic, few groups work on it, and so yeah, it takes time to progress. But still, in a decade, we went from very manual to completely automatic. So now, nowadays, people ask me, well, this is all based on optimization. Why don't you use machine learning? And we also did some work on that. So for instance, here I'm showing some methods we developed that takes one or several drawings as inputs in a bitmap format, feed them to a convolutional neural network, and automatically predict a volume, a voxel grid. And here I'm showing another work we did with Chengjian Li, who is hosting me here at the University of Edinburgh, where we trained machine learning systems to recognize basic shapes in drawings, so cylinders, cubes, and predict their dimensions. And so we can turn a drawing like the one on the left into a sequence of modeling operations where basically we reconstruct the shape as a small cylinder with a bigger cylinder on top and a cube, and then remove another cylinder. So this gives a parametric representation of the shape where the dimensions can then be edited. So if the 3D, if the user now wants the same hammer but with a thicker handle, they can just change the radius of the cylinder. They don't have to redraw it. So this is promising, but really what makes this machine learning strategy challenging is that compared to photographs where there are massive data sets online, we have very little training data, to the point where actually there's no real data much for training this type of system. It would be impossible to ask designers to draw thousands and thousands of shapes. So what we used to train those systems is synthetic drawings. So using computer graphics techniques, we can render 3D shapes as line drawings and then train the machine learning model to solve the opposite tasks, given that line drawing recover the 3D shape. But existing algorithms only detect contours and silhouettes. So the drawings we can synthesize don't really look like the drawings that designers will create. And there's still this huge domain gap. So we also did some work on that with Chengjian Li. So we proposed an algorithm that will actually mimic the techniques that designers employ to create plausible synthetic drawing sequences with construction lines and so on. So it's a step in that direction, but it's still synthetic. So in my opinion, I think we need to progress both on this type of method to really create large data sets, but we also need to collect more real drawings to bridge this domain gap. So this is more ongoing work. Like we haven't tried yet to use this type of synthetic data to train those models. But in parallel, while until recently I was really convinced that we needed this type of drawing data sets to train for 3D reconstruction, I was very impressed when I tried to apply very recent reconstruction models to drawings. So here I'm showing rigidity, which is a system that's been published recently. Actually, it was presented here a few weeks ago. That's been trained to take one or several images as inputs and predicts lots of 3D data. So the camera pose, depth map, point clouds. And it's been trained on massive data sets, lots of multi-view reconstruction data sets, video games, 3D assets. And I think because of this massive and diverse training, it actually works decently on line drawings. So we just took rigidity out of the box, we fed it line drawings, and we obtained very good reconstructions competitive with what we achieved through optimization, which suggests that actually maybe we don't need massive line drawing data sets. Maybe pre-training on photographs is a good first stage, and then we could fine-tune on line drawings. So that's, again, not done yet, but I think it's plausible. It doesn't mean that we can completely forget about optimization. The reconstruction is good, but a bit distorted. So ultimately, I think that the two strategies would be complementary, like machine learning to get an initial guess, but optimization to really impose regularities. So that concludes my talk. I wanted to thank my collaborators, and in particular, Yulia Graditskaya, who collected the data set I presented and implemented the first automatic algorithm, and Felix Heinlein, who developed the symmetry-based algorithm, which to me is a state-of-the-art in terms of optimization-based methods. Thanks for your attention, and if you have any questions. Naive question probably
the prior explanation that included learning, the initial process.
Sorry,
As it okay. I will repeat it and revise. No.
Just turn on. Correct.
Like we interpret the shapes when we look at it in front of the shapes, we try to reason it. But in the prior equation, there's only that decision. That's the only prior that we. So we used intersections, orthogonality, parallelism, symmetry. But I agree that all of those are geometric relationships between strokes. So it's very low level geometric relationships. We don't use higher level priors like, oh, this is a cylinder, this is a cube. We did with our machine learning approaches. We trained methods to recognize geometric primitives, but in the optimization-based methods I presented, it's mostly very low level geometric relationships. The reason why I think it's good to go that way is that it gives more freedom to the designer. They don't have to draw geometric shapes that are like a specific set of geometric shapes. They can draw quite arbitrary surfaces as long as there are some intersection, symmetry, or parallelism, we can exploit it. So that's the trade-off. The more you go into recognizing higher level primitives, you'll be more robust, but you'll have less freedom on creating new shapes that were not observed in your data set, let's say. So that's a bit of a balance between the two.
That's leads to my next question. So, in reality, the professional designer try to render everything, every detail, but try to be very comprehensive. But in reality, we are trying to use it for more offering a tool or something like that for non-professional designers, like usual drawing. That becomes quite incomplete, even sometimes even like they don't follow the same rules that the designer follows.
Yeah.
Is there any future research that would look into something like this, incomplete drawing or something that would actually be able to interpret the figure, but by just a simple sketch that even maybe just recognizing this is a TV. I know this is a TV. So it's just enough to few features just to know that this is what I need.
Yeah, definitely, and not just for novices. Even in design, people do different types of drawings at different stages. So very early on, when they want to explore lots of ideas, they do what they call ideation sketches. And often they are very incomplete and ambiguous, which is a good thing, because if a drawing can have several interpretations, it stimulates creativity. And that's not the type of drawing we can reconstruct with the methods I presented. Later on, once they have a definite idea of what they want to build, they will draw very accurate drawings, and that's what we targeted. Now, indeed, to reconstruct those other types of drawings that are more abstract, more incomplete, then I think the data-driven methods are better suited, because you need to fill in the gaps, and this is more of a generative problem. And actually, you don't even want a single interpretation. You might want a distribution of interpretations, because since there's ambiguity, there's no single answer. And that's where the data-driven methods have been definitely very successful. So there are indeed systems that target more novices, where you vaguely draw the outline of a shape, and it creates a very good chair or a very good car, but it hallucinates details. So this is not, it's not targeting the same type of application, but definitely it exists.
Because the hallucination also is restricted by some restraint from the original drawing. So hallucination, yes, but also it has some restriction. So it cannot change, for example, that this the overshape.
Yeah. So this has been done. Until very recently, the systems based on machine learning that could do what you described were limited to the data set they were trained on. So you could have very good systems to draw chairs and airplanes. That's what you will see. But since a year or two, there's been those very large 3D model data set like Observers. And so now there are systems that can indeed turn a single drawing into a very detailed shape, even though the drawing is quite approximate. But that's only possible with massive data sets, I think.
We do have two questions online from our audience. The first one is, how do you envision the adoption of this technology in industry's automotive architecture with consumer electronics? Are there any foreseeable challenges or issues that need to be addressed?
Right. So I think there's definitely a demand. Every time I talk to either designers or companies doing software for designers, they do say that there's a gap between the drawings people draw very freely and the 3D models they want to create with digital tools. But so far, this gap has not been filled for several reasons. One is that it's very hard to compete with the freedom of drawings. There's been some system like I Love Sketch that I presented very early on, or Autodesk, for instance. Dassault has a system called Natural Sketch. But those systems impose a bit of restriction on the user interface, and that's enough for designers to say, oh, no, I don't want to learn yet another tool. I don't want to be restricted. So I think for those tools to be really adopted by the designers, they want to offer as much freedom as freehand drawing. And unfortunately, it's very hard to achieve. So the systems I presented, they did progress in that direction. The last method I presented is automatic. But it doesn't always work very well. You have strokes that are misplaced. And for some drawings that are not as regular as the ones I presented, the reconstruction is not usable at all. It's so distorted that you cannot do anything with it. So if it only works half of the time, the designers will also say, I don't need that. I want something that always works. So I think that's really the blocking point. There's a need. People would like to have such a tool, but until it's completely automatic and offers complete freedom, they will be very reluctant in adopting it. That's maybe why novices is a better audience to target, because they have lower expectation on the quality, and they will also tolerate that the algorithm creates stuff they didn't want to create. When designers draw, they would like the model to perfectly agree with their drawing. And that's where data-driven methods, sometimes you have no guarantee. Like it could create something that deviates too much from the input.
And also we have another question coming from another student said, will the system be able to integrate with the traditional CAD tools and design platforms widely used in industries? How would it complement existing software? Could it reduce the dependency on highly skilled experts?
Yeah, definitely. So that's exactly the topic we've been researching with Cheng and Li. Actually, if I can go back in my slides. This was the goal of what I present on that slide. It's to convert a drawing into CAD commands. The motivation was that CAD is very powerful, but it needs indeed high expertise to not only know where to find the operations in the software, but also know what operation should be used to reach the shape you have in mind. And so the goal of our research, which is still ongoing, and we're not the only one to work on that, is to automatically translate a drawing or some other modalities expressed in a language that is accessible for the user. Let's say a drawing is very easy to do, into the language of CAD, which is what is shown here. It's like almost a programming language. And that's where machine learning has been helpful. We actually casted it as a translation problem, and we use transformers for that. So you have a drawing sequence as input, you want a modeling sequence as output, and indeed, ideally, it would lower the entry level for CAD design. So the system is called Sketch to CAD. So it's really from Sketch to CAD.
My question is, as we understand in the 3D algorithm, they always talk about the principle. Here is more like the principle and the information you add on to the current system. If it means like the world model concept, they can automatically grasp on principle or particular into the current system, not only like the current design and to make it like more comprehensive.
Right. So how to inject more principles and how to find them in a sense. Indeed. So the methodology I presented really starts with us studying the design literature, identifying principles that are well suited for geometric optimization and so on. And so that's a very interesting process for us researchers, because I learned a lot about drawings by doing it. But it will have to be done for every new domain. So we mainly studied the principles of product design, and now if we want to develop a system for fashion design, I have to go back and interview fashion designers and study fashion design books. So this is indeed quite constraining. Ideally, I agree. If we could discover those principles or let them emerge from, I don't know, data in a sense, that would be excellent, but I don't have very concrete ideas on how to do it. In this work, we really adopted more of like we discovered the principles ourselves. Yeah. Thank you.
There will be and then there's some comment.
Thank you.
Thank you. And just something.
Thanks.